Hello and welcome. This is the first installment of my new series, How to Reverse Engineer, with a heavy focus on the tool angr. For this series, I'll assume some basic understanding of the underlying concepts of reverse engineering, but hopefully there will be something for everyone. So to begin, we're going to be looking at challenges that were as a part of the ACI CTF competition. So if you don't want spoilers, this is your spoiler warning. So what I've done is I've collected a select few of the reverse engineering problems, and I've archived what my version of the challenges were into these folders. And I was thinking I would just make a video for each of them talking about how I solved it. And when applicable, we will use angr. And then I think there will be an eighth one that's not shown here, which will be how to solve a assembly programming challenge where you can essentially use angr as an emulator to emulate multiple architectures, which was very convenient for solving that challenge. So for now, here we are. Let's go to reverse engineering. And as you can see, inside this folder, I have the description of the problem and then the original binary. So if I just say file on the binary, you can see that we are given a 32-bit ELF binary. And then let's open up our description file, and I'll read it here. It says, reverse engineering can definitely be intimidating, so we have a simple program with which you can start. If you don't know where to start, check out the hints, and we'll walk you through two different ways to solve this problem. So in this context, in almost every single reverse engineering problems, whether I know ahead of time that I'm going to want to use angr or not, the very first thing that I do is I attempt to open up the problem in Ghidra. And the reason is, a lot of times there can be little details that you'll find right away just by glancing it over. So I really take this breadth first search approach to mind, where I'll go down each of the paths, static analysis, dynamic analysis, a little bit, just so that I know a little bit about the environment that I'm in. And then after that, I'll make a decision about what I want to do. Okay, so if you weren't paying attention, I imported my project, and then I went immediately to this functions category here after doing the brief Ghidra analysis, and I clicked on the entry function because I don't have a lot of choices. So and then you can see pretty clearly right here what's happening is we enter the function, it loads this flag variable, and then it assigns a bunch of values, and then at the very end it exits. So what we really want to do is just probably see what all of these values become at the end. So this isn't a problem where I would normally use angr. I might just put this in GDB. So I'll probably just show two strategies here. So first let's open it up in GDB. And if I say start, it just puts me right at the very beginning, and then I can just stop right before this interrupt at the end here. So I just pasted the Ghidra, Ghidra value there. And now we can continue, and it'll bring me all the way to that interrupt, which you can see here in the code context. And now all I want to know is what's in this buffer right here. So, and boom. All right, so that got us our flag. Okay, but that's not why you're here. You're here to learn how to use angr. So the first thing that I'm going to do is launch an angr instance. And it's really quite difficult to install angr, so instead of doing that, we're going to use Docker. If you don't know how to use Docker, I recommend you at least learn a little bit just for the purpose of following along. So what we're going to do is mount our local folder, which is like this one reverse engineering 101 folder. We're going to mount it inside our Docker container in the /local folder, and we're going to run the angr/angr container. So now here I am, and this is great. Angr is already set up, so I can just say cd/local. And if you don't have the angr container, but you run this command, it'll pull the angr container for you, so it's quite easy to set up. So now we're going to jump into IPython, which is an absolutely amazing tool for learning how to use angr, because you can tab complete things and you can very quickly see help menus, so very helpful. And even having used angr for quite a few years now, I still use it this way. The interface is changing very frequently and I forget things, so it's really helpful. So the first thing that we want to do now is import angr, and this will let us make a project. So we can say angr.project, capital P. And then we also have this nice feature of IPython, which will let you tab complete files even. So we can do this original re101. All right, so now that's going to make a project for us, which is fantastic. So if I say p dot and then I hit tab, now I can see all the options that I have available to me. The one that we're really interested in is this factory thing, because it lets us make like a new state. And if you're not too familiar, basically a state is a lot like in GEB, how we set a breakpoint at the interrupt at the very end of the program. And when you get to the interrupt, you've built up all of this data in the program's memory. You've built up a state of how the program is supposed to be behaving, and so that's why we call it a state. And so what we can do is we can have an entry state, which is like right at the very beginning of the program, you have some stuff available to you. Things that are set up by libc, for example. So here we are at the entry state, and I set it to S. And this is also a good time because I will very frequently use other tools to talk about logging. So if I import Python logging library, we can set a little bit more logging for the angr thing, so you can see we can talk a little more about what's happening behind the scenes. Git logger angr, and then we can set level logging.info. You can set it to debug, but it's a lot, so we're just going to go with info for now. Okay, so now if I click S, I have what they call a symbolic state, which is a little misleading because right now there's nothing symbolic in it. It's a concrete state at the entry point. There's no introduction of user data, so there's no really reason for this to have divergence paths or anything like that. It's just, it is what it is at the very entry state. And so now what we want to do is we want to get this state to the breakpoint. So if I open up Ghidra here, right now we're somewhere we can actually look. S.adder. Helps if I can actually read the values. So we're here. I can paste this into Ghidra. Boom. Okay, we're at entry. Right here, perfect, at the very beginning of the function. And so where we want to be is right here, this interrupt place. So I'm going to copy that value, and we're going to use it in a second. So in order to get there, there's a couple ways that we can do that. We can interact with the state directly, and essentially what happens is the angr engine will lift a code of instructions, and it will change that instructions from its current language, which is right now is some 32-bit Intel, into a intermediate representation, which angr uses vex. And we can take a look at that. We can say s.block, which is the current program block that we're in right now, and we can say vex. Right? And so, okay, I think there's a way to more easily see that. So what I've dumped here is the vex intermediate representation in printable form. And so you can see, oh, at this instruction, we're going to put some value into EIP, and then at this instruction, we're going to set less than equal to this address, this value. So we're assigning memory right there. Okay, and so, yeah, well, I'm not going to walk through this whole thing, but that's basically what's going on. And if I wanted to see it in like a language I'm probably more comfortable with, I can say capstone, I think. Let's see, vex. No. So what I want to do is use my tab complete here, like I was talking about earlier. So b.tab, and then their stuff. And capstone is the engine that they're using to lift. And if I extract that object, I can see what the original bytes were. And there it is. There's this block. And the reason why it all prints out at one time, instead of being split up like what you might see in IDA, is because there's no branching instructions here. Everything has to happen sequentially until you get to that interrupt. So in IDA, this is probably exactly what the block would be in the entry function. So now what we want to do is run this block. And the way that you do that is you call step on the function, on the state. So here's my state, right? And if I say s.tab, it prints a bunch of debugging stuff, so we'll do that again. So s.tab, and there's this step function. And there it is. So I can just tab right to it. And now what happens is angr will run the program. It will emulate the program until it gets to the end of the block. And at the end of the block, it will tell you, well, there's only one place for me to go. I can't, it's not a branch like that can take two directions or n many directions. It's an indirectional, a thing that has to always happen. And so here, the only place that we can go is to this next block right here. And that's what it's trying to tell me. So, but my original state hasn't changed, right? I'm still in that original address, B8, which is right here, the beginning of my entry function. So I haven't modified the original state. It's not mutated at all, but I can get where I'm supposed to go after that. Okay, and that can be nice in certain circumstances to be able to control a state that finely that you can say, we're going to step one block at a time. But they've also added a set of tools to help do that for you, where when you step and you have new states, well, now you probably want to step all of those states, and it gets more and more complicated, right? So they have a simulation manager, which will manage all of those states and stepping them all at the same time for you. So, and that's called a simulation manager. So the way that we're going to get that is we go to the project.factory, just like we were before, and there's this simulation manager. So if I hit question mark, which is another great tool of IPython, I can see the signature here. So what we're looking at is that the simulation manager can take in a state, but it can also just build the entry state for you. So we have S here, our built state, but just to show you, I could just make it empty, and now I have a simulation manager. And it tells me that there's one active state. So if we say simulation manager.active, it'll give me the list of all the states. So there it is, boom. So I can say sm.step, which will do, it'll step every state in the active queue. And now sm.active contains a new state, right? New one right there. And so let's play around with that. And so now in this state, what I want to do is inspect the memory that's at the flag address, right? I want to see what all was stored there. So we're going to say s.mem. Oops. And we can give it a square bracket, and we'll give it the address. Paste that in there. And now it says, oh, well, I don't know what type this is, so we can specify. There it is, our string. And you might be saying, well, that looks really weird. It's a really long, this stands for bit vector, a bit vector of 168 bits at this address. Like, it's not very easy for us to read, right? So let's save that to a value. We'll call it flag. And now flag is our really weird bit vector. So there's two ways we can approach this. I'll take the more Python way first, which is that I can import binascii and say binascii.unhexify, and I can paste this in and be super cheap. Okay, let's do that really quick. And there's our flag. But I can also do this the more angr way. If I say flag.concrete, I can get the concrete version of our flag string. And that's all.